Hello everyone. In this project, this self-balancing robot was built using the LEGO MINDSTORMS EV3 robot kit and the EV3 gyro sensor by following this guide by Robot Square. Like the Robot Square IQ project, I call this robot the LEGO EV3 Segway because like a real-life Segway, which is a two-wheeled self-balancing vehicle used for personal transportation. The robot also balances itself on two wheels. The Segway code is written in MicroPython using EV3 MicroPython, which runs on top of the EV3 Dev operating system. The code is a modified version of the LEGO Education Gyro project. The robot can be controlled in two ways. There is directional control from a Node-RED flow with the Segway as an MQTT client. Commands to move forward, backward, turn left or right can be sent to the Segway via an mqtt-broker. I call this control method mqtt mode. And secondly, tether control using the EV3 infrared sensor and beacon. Here the Segway follows the beacon by rotating to reduce the angle between them to less than 10 degrees. Then it translates towards the beacon until it gets close to it and stops. I refer to it as tether control because it looks like, at least to me, that the Segway is connected to a cable as it follows the beacon. This is the beacon mode. My goal with this project was to learn about MQTT, Node-RED, and MicroPython, and share what I've learned with you. There are video chapters available you can skip to. Let's start out with the hardware setup and software installation. There is a guide made available by LEGO Education on how you can get started with programming in MicroPython. These are the things we'll need. A Windows or Mac OS computer, but this also works with Linux because I'm using Ubuntu. Internet and admin access on the computer. A microSD card with a minimum capacity of 4 GB and a max of 32 GB. We'll also need a microSD card reader to flash the EV3 MicroPython image on the microSD card. This could be an inbuilt one on your computer or an external USB card reader. They also listed a mini USB cable, but this is only required if you want to connect the EV3 brick directly to your computer. We won't be using the cable because we'll connect to the EV3 wirelessly using SSH. This next part is software related, so we'll come back to it in a bit. Still sticking with hardware, we obviously need the EV3 kit for the project. These are the two kit options. There's the LEGO MINDSTORMS EV3 Education Kit and the LEGO MINDSTORMS EV3 Home Kit. I have the EV3 Home Kit which doesn't have the gyroscopic sensor, but the education kit does, so I had to buy the gyro sensor separately. The gyro sensor is required for the Segway to read the angular velocity of the robot. This value is used in an equation to balance the Segway. The final hardware we need is a wireless or Wi-Fi dongle because we will be communicating with the Segway wirelessly via SSH from the PC. The dongle I'm using is by Edimax, but there are some other options to choose from. Going over to the EV3 Dev website under networking, there's a list of recommended dongles that are compatible with the EV3. The dongle is also necessary if you want to install new software on the EV3. Okay, now we've got the EV3 kit, gyro sensor, and Wi-Fi dongle. The next thing we need to do is to assemble the robot. As I stated in the intro, I'm using this build guide from Robot Square for their Balancer robot. It's very straightforward and just requires some patience. You can also find the build instructions here. Just in case the Robot Square website is down. I experienced some issues accessing their websites a while back. The instructions aren't in English, but that shouldn't be a problem. We're only concerned with the pictures. All of these links will be available in the video description. I want to briefly go over two image options that you can flash on the EV3 brick. On the top left, we have EV3 MicroPython. This is an image option made available by LEGO. Beside it is EV3 Dev Python, an image developed by EV3 Dev. These image options are built on top of the EV3 Dev operating system, which is a derivative of the Debian Linux operating system. From the image names, it's obvious what programming languages that are used. MicroPython for the EV3 MicroPython image, and Python for the EV3 Dev Python image. The only reason why I chose to use the EV3 MicroPython image is because I have another project I'm working on which will use MicroPython, so I wanted to get familiar with it. MicroPython.org defines MicroPython as a linear Python implementation that is optimized to run on microcontrollers and in constrained environments. Now that we understand the image options, let's go back to the LEGO installation tab. We can write MicroPython programs for the EV3 using Visual Studio Code, and these were the steps to set things up. However, I had issues maintaining a stable connection to the EV3 with this method. Instead, we'll edit programs or install any packages for the EV3 using an editor on our computer via SSH. This is the EV3 MicroPython image file we'll need to download and then flash onto the microSD card. We'll use Balena Etcher to do that. Click on download. Then download the version for the OS you're using. I already have this installed on my computer. I also have the image file downloaded. So you just need to plug in your microSD card into your PC, which I've done. Open up Balena Etcher and follow the steps on screen to flash the image. With the image flashed, let's insert the microSD card into the microSD card slot on the EV3 brick and boot it up. I've also plugged in the Wi-Fi dongle. Let's boot it up. It does take a while to boot up. So this is the main menu. You have the file browser, device browser, wireless and networks, battery, open Roberta lab, and about. But we want to set up the Wi-Fi, so I'm going to go to wireless and networks. And come down to Wi-Fi, and click on power. So this is going to turn on Wi-Fi scanning. So now we can click on. So if you can see here, the item access blinking. Okay, so it's picked up my network, so I'm going to click on this and connect. Alright, so it's connected now. So up top you get an IP address. So now that we're done with the Wi-Fi, we can move back to the computer and set up SSH to be able to connect to the EV3. With the network connection set up, the next thing we're going to do is configure an SSH connection to the EV3. This will enable us to send commands to the robot over the network to run programs, change settings, and install packages. We also need SSH configure to clone the project repository. We'll follow this EV3 dev guide to set up the SSH connection. There are different instructions depending on the OS you're using. I'm using Ubuntu, so I'll use that. So the first thing I'm going to do is to copy this command, which we'll use to connect to the EV3. And open the terminal window. And then paste the command we just copied and run it. So if this is your first time running this command, you'll be prompted to confirm the authenticity of the host. Just like what's being shown here. So in this case, you just need to type in yes to continue. I've done this already, so now the only thing I need to type in is a password. And the default password is maker. So put that in here. Now we're in. So now we can clone the project repository. So going over here to the priority page, we're going to click on code and copy the HTTPS link. And type in git clone and paste the link we just copied and click on enter. But I get this error whenever I try cloning the repository, even on my main computer. I've changed Wi-Fi networks, redecided the file in the repo, and also tried increasing the Git buffer size, but the issue still remains. I'm open to suggestions on how to fix this, and hopefully it's not an issue for you. As an alternative, I'm going to download a zipped form of the repository, then set it to the Segway to be unzipped. So we can do that by clicking on this button here to download the zip file. I've already downloaded it, so it's in my downloads folder. So the next thing we're going to do is to transfer the zipped repository to the Segway. But before we do that, we need to know what the IP address is of the Segway. So I'm using this program. It's called Angry IP Scanner to do that. The different versions for Linux, Windows, macOS. So I'm just going to open that and show you how it works. Oops. So just go over here, click on Start, and scan. Okay, so just going to scroll through, and you can see here this is the EV3, and this is the IP address 192.168.8.218. So now I'm going to open another terminal, and since I already have this downloaded, I have the zip file downloaded. I'm going to navigate to my downloads directory, and I'll run this command to send the zip file to the EV3. And they're asking us for the password, which is maker. Okay, so since it's done, now that it's done, we can go back to the Segway terminal to unzip the repository. So let's just confirm that it's in here. So click on ls, and you can see we have that here. So to unzip the file, I'm going to type in this command, unzip it. Alright, so now we have both the directory and the zip file. So we can delete the zip file with this command. Okay, so let's jump back to the Segway to browse through the project files. So click on the file browser, then open the project folder. These are the different files in here, but the most important file is this main.py Python script. It starts out the balancing loop, the MQTT and beacon mode for the Segway. We run it by simply clicking on this middle gray button. But before we do that, we need to install MQTT and Node-RED on the computer, then go over the steps of the script. What is MQTT? MQTT stands for Messaging Queuing Telemetry Transport, and it's a protocol commonly used for message exchange between devices, sensors, computers, and more. It's a simple and lighter protocol ideal for resource-constrained devices and unreliable networks. It's a de facto standard for messaging between IoT devices. MQTT uses the publish-subscribe architecture, which I will briefly explain using an email newsletter analogy. So suppose you're interested in space. One way to stay informed would be to subscribe to a popular space email newsletter. You go over to their website, type in your email address, and sign up for the newsletter. If it's a bi-weekly newsletter, the author will publish a new edition of the newsletter every 2 weeks to her list of email subscribers. The email service provider receives this newly published edition of the newsletter and sends it to the inboxes of the subscribers. This is similar to how MQTT works. MQTT has two main components, client and broker. Client can publish a message on a topic which is sent to the broker. The broker sends this message to another client subscribed to the same topic. The MQTT broker acts as an intermediary between devices by dispatching messages published on a topic from one client to other clients that are subscribed to the same topic. Additionally, the broker handles client authentication and authorization. So in this diagram here, we have three MQTT clients. The temperature sensor is the publisher, while the laptop and the mobile phone are subscribers. The temperature sensor publishes temperature messages on the room temp topic, in this case 25 degrees Celsius. And the laptop and mobile phone subscribe to get this temperature data on the same room temp topic. For this project, the MQTT clients are Node-RED and the Segway, which has a lightweight MQTT client, which I think is called micro-MQTT. It's spelled UMQTT, so I'm guessing the U is the Greek letter mu, which is packaged in the EV3 MicroPython image. The MQTT broker we're going to use is Mosquitto, which we're going to install on the PC. I've included some MQTT related links in the video description. Now with the overview out of the way, let's install MQTT and Node-RED on the computer. The Mosquitto broker can be installed on a number of operating systems. It's available in Ubuntu, so you can install it easily by running this command. I already have it installed on my computer. The installed broker comes with MQTT clients that can be used to publish and subscribe to topics on the command line. We'll get back to this later once we have Node-RED installed. So Node-RED is a flow-based programming tool that makes the process of connecting hardware devices, APIs, and online services easier. It has built-in support for MQTT and can be installed on a number of operating systems or platforms. So Node-RED can be installed by running this script. Even though it's on the Raspberry Pi, as it says here, the script will work on any Debian-based operating system, including Ubuntu and DiPi. So if you were to run this, I already have this installed, but once you have it downloaded, you can start Node-RED by running this command. And this is going to spin up a local server which can be accessed by opening this link in the browser. So the reason we're having errors here is because I need to set up the broker connection, which we're going to do shortly. So if you click on this, this not right now. This is the flow we're going to use to send commands to control the Segway. For now, we'll set up a simple flow to learn how to use the MQTT clients on Node-RED to subscribe and publish the topics with the mosquitto-broker MQTT clients. Let's open a new flow by clicking this plus button and quickly go over the Node-RED components before setting up a simple flow. So Node-RED has 4 main components. The first one is a node palette. That's this section over here, which has different nodes you can use to create your flows. They're grouped into different categories, and you can search for a particular node using this search option here. The next component is the main workspace. This is where you create your flows by dragging nodes from the palette and wiring them together, which just means connecting the nodes together. So it's going to bring out this MQTT in node and the debug node. And thirdly, there is the header up top, which contains a deploy button, which you click to send your current flow configuration to the Node-RED runtime. The different options for the deploy type you might need. The other part of the header is this menu, which has a lot of options in Node-RED like importing, exporting, search and flow, product management, and more. The final components is a sidebar. That's the section here. There are a number of tabs here used for different purposes, like getting information about the current selection of nodes. So in this case, MQTT in node gives us some small summary about it. Then there's also the help tab, which gives a documentation on the MQTT in node in this instance. Then we also have the debug tab, used to see the messages sent to the nodes and if there are any warnings or errors encountered. We'll leave the sidebar in the debug tab to show the messages that are published by the MQTT clients. I've included a link in the description to know more about the essentials of Node-RED. Now let's create a basic flow to test out the MQTT connections. We'll start out with this subscriber test. For this, we're going to use the MQTT in and debug nodes, which I have already dragged out, and wire them together. So to wire them, we just need to click on this button and drag to the other end. I'm also going to drag out the comment node, just to know what we're doing and give it a name. We'll call it mosquitto subscriber test. Alright. Next thing we're going to do is to set up the connection to the mosquitto-mqtt-broker. So double click on the MQTT in node, then click on this plus button beside the server field. Let's give the broker name. We'll just call it mosquitto-mqtt-broker. The server field is the PC IP address Mosquitto is installed on. So mine is 192.168.8.193. Then we'll click on add. We need to choose the topic we want to subscribe to. So let's subscribe to topic test/topic. Then click on done. Then on the deploy button to effect the changes. We haven't set up the MQTT connections for flow 1 that connects to the Segway. We'll get to that later, but for now just click on the confirm deploy. Yeah, so let's also close this, clear it all for now. So disconnected text signifies that the connection has been established with the Mosquitto broker, but we'll confirm that by publishing a message from the Mosquitto pub client. So let's open a new terminal window and type in Mosquitto pub. So we're going to, the topic we're going to publish on is test/topic, and the message we're going to send is hello from Mosquitto. So we can see the message we published in the debug tab, which shows that the node read MQTT in node subscriber node received the message. Let's also confirm that we can publish from node read to the Mosquitto sub MQTT client. Let's put this here. So for that we're going to just put this on top. We need two nodes. We need an injection node and this MQTT output node. This should be here. And just connect them together. Then let's going to drag out another comment node and name it Mosquitto publisher test. We'll set up the MQTT alt node to use the server we just set up. So just double click on this and click on server and click on mqtt-broker. Then we also need to type out the topic we want to publish to. So let's publish to the same topic from before. Then click on done. In the injection node, we want to set up what message to send and the type of message to send. But let's give it a name. Let's call it publisher test. Then in the payload, so the different types of messages that can be injected to a flow. So we're just going to look for a string. I'm going to send a string. And the message we want to send, so let's say hello from node red. Then the topic is going to be test/topic. I'll click on done, then also on deploy. So let's going to clear this again. Okay. So now in the terminal window, we're going to type in Mosquitto sub. So we're subscribing to the test/topic. And click on enter. Now we just need to click on this button here to inject the message to the MQTT alt node. So we successfully got the message published from node red. And it's also on the debug tab. Before proceeding to go over the main program, let's correct the configuration error for flow 1. So just come over here. So what we need to do is to change the server configuration for the MQTT nodes. That's these ones that have the red triangles on top. So in the server field is going to just click down here, then click on mqtt-broker and click on done. So just to give you a glimpse of what we're going to use later on. So if you click on this injection node, turn left. So this is going to inject a string payload on the node red/command topic. This is turn left. So once the segway receives turn left, it's going to execute that action, which I will get to later on. Alright, so let's do the rest. Come down here, mqtt-broker. And click on deploy to effect the changes. So everything is working well now since we have the connected texts underneath each mqtt node. The other thing we need to do is to make a few adjustments to the mosquitto config file. We need to do this to ensure that the segway can connect to the mosquitto-broker without any authentication requirements. Mosquitto is installed on Ubuntu as a systemd service, so we need to stop the service before making changes to the config file. So let's open up a new terminal and type in this command to do that. systemctl stop mosquitto service. Then put in your password. Now open up the mosquitto.conf file with an editor with admin privileges. I'm using vim, so you can type out vim etc this. And put in your password again. So these are the lines that you need to add to the config file. Since they're already here, just need to close and save. Just want to mention that all of these steps are detailed in the project GitHub README. Now that that's done, let's restart the Mosquitto service with this command: systemctl start mosquitto.service. Oops. Then we can confirm that it's running by typing out system status mosquitto. We can see the mosquitto is running. And if you also notice in the background, in the Node-RED window, these connected blocks were red at a point, but now that it's green, it also confirms that the broker is running. These publish action commands use the same nodes we tested out in Flow 2. Just in this case, we're publishing commands to the Node-RED/commands topic to control the segway. There's also a subscription test here to confirm that the segway's MQTT connection has been set up correctly. I've turned on the segway again. So what we're going to do, we're going to navigate to the file browser, then into the project directory, and scroll down to the main.py script. This script does a lot of things, but we're concerned with it publishing a message to the Node-RED/commands topic to confirm that the connection has been established between it and the mqtt-broker. So we're going to click on this button to run it. And you can see over here in Node-RED, we have this message, publishing test. Oops. And we can see over here in Node-RED that we have this message, publishing test. This was sent from the segway, so we can confirm that the connection was established between it and the mqtt-broker. Now that we've confirmed that the segway can communicate to Node-RED via Mosquitto, let's delve into the main program. Like I mentioned in the intro, the code for the segway is modified from the LEGO Education Gyro project. which balances the gyro boy on its two wheels by making use of the EV3 sensor. And that's the program that was modified. So I closed most of the tabs just to reduce the clutter. The main.py Python script contains almost 300 lines of codes, but with a lot of helpful comments. I went into more detail explaining certain parts of the code in the README. However, the major parts of the program are summarized in this flowchart. The program starts by initializing the EV3 brick, the two motors, the infrared and gyro sensors, and various constants and variables. Some of these variables include a number of timers. The loop timers are used to measure the time it takes to complete a loop, which will be utilized in the control feedback calculation. The fall timer is used to confirm that the robot has fallen over. I'll touch more on this later on. And finally, the action timer is used to execute a particular action, which I will explain shortly, for a specified number of seconds. There is also a named tuple called action used to define the drive speed and steering values for particular robot actions. As your names imply, drive speed determines how fast the robot moves forward or backwards, while steering is how fast the robot turns left or right. Considering the backward action, for instance, the drive speed value is -60, with a steering value of 0. The name tuple is a container data type in the collections module that provides alternatives to the common Python built-in containers, which are dictionaries, lists, sets, and tuples. The drive speed and steering values are used later in the control feedback calculation to compute the output power of the motors needed to balance the segway when it's in motion or in a stationary position. Another set of variables that are initialized is the dictionary of node-read command states. The states are all initialized as false, but when a command is received from node-read, the corresponding command state is set to true, with the respective action executed by the segway. The MQTT connection is also set up as we touched on earlier. This code snippet shows the procedure the segway uses to establish an MQTT connection with Mosquitto, where the broker constant is the IP address of the MQTT broker. The micro-MQTT client subscribes to the topic node-read commands to receive messages from node-read, and to test its MQTT connection, it publishes the message publishing tests on the same topic which we saw a while ago. Before we step into the main program loop, we have to define the update action generator function. But what is a generator function? A Python generator function is a function that returns a lazy iterator or an on-demand iterable object. These objects can be looped over like a list. However, unlike lists, lazy iterators do not store their content in memory. A generator function, or simply a generator, differs from a normal Python function as it uses a yield statement instead of the return statement. So let's consider this simple script in VS Code. We have a simple generator function called generator test, and we have a number of print statements. So let's run the program, then I'll explain parts of the code and the output. Okay, so on line 7, when the generator function is called, it doesn't execute the function body immediately. Instead, it returns a generator object which was printed out here with a print function on line 9. The yield keyword produces the value from the generator. The next function loops over the objects and outputs the yielded numbers 1, 2, and 5 from the print functions on lines 10 to 12. When a generator calls yield, it's momentarily passing control back to the code looping over the generator values. The next function then passes control to the generator, which yields a value back. This exchange of control continues until there are no more yields in the generator. This video from Socratica is a very good introduction to generators.
And I am now going to talk about generators.
The link is included in the description. We'll go over the object action generator by looking at the different segue modes. But for reference, this is where the generator is defined in the code. We're here at the moment. The object action generator contains the MQTT and beacon modes of operation. In the MQTT mode, the object action generator checks for directional control messages from Node-RED forwarded by the mosquitto-broker on the Node-RED/commands topic. Remember that the Node-RED command states are all initialized as false. So if Node-RED injects the command turn left, for example, on the Node-RED commands topic, this particular command is now true. The drive speed and steering values are updated with this predefined robot action we initialized earlier with the command yield turn left in this instance. These values are looped over by the main program control loop and used to calculate the output power of the motors. The segway will turn left for 3 seconds before stopping by yielding the stop robot action. If all the command states are false or after all the command state checks are done, the beacon mode code block is executed. In the beacon mode, the segway follows the infrared beacon by rotating if the angle between them is greater than 10 degrees, translating towards the beacon when the angle is less than 10 degrees, and stops when the segway gets close to the beacon. To enable tether control of the segway, the beacon has to be turned on, set to channel 1, and be within range of the infrared sensor. This flowchart describes the steps for setting up tether control of the segway in beacon mode. The first step is to confirm that the relative distance value is not none. The beacon is used to measure the relative distance and angle between the EV3's infrared sensor and the beacon. The relative distance ranges from 0 to 100, while the angle is an approximate value between -75 to 75 degrees between sensor and beacon. If the relative distance is none, which means that the beacon isn't detected by the infrared sensor, the yield keyword is used to pass control to the main program control loop. This is to ensure that no function calls are made that would affect the control loop time in the main program. Otherwise, a proportional controller, which is a variant of the proportional integral derivative controller or PID controller, is utilized in calculating the steering value of the action name tuple. This is obtained by multiplying the angle error term, which is the difference between 0 and the obtained angle from the beacon, by the controller gain or constant, attained through experimentation. The drive speed is set to 0 in the newly formed action. This action is passed to the main program loop to calculate the motor output power required to reduce the angle between the segway and the beacon, thus rotating the robot. As the robot rotates towards the beacon, if the angle error is less than 10 degrees, a proportional derivative controller, another PID controller variation, is used to calculate the drive speed value for a new robot action. In this case, the error term is the difference between 100 and the relative distance obtained from the beacon. Similarly, the proportional controller multiplies this error with the controller gain, which is added to the derivative controller, which multiplies the change in the error over time by its controller gain. The steering value is set to 0, and the action is yielded to the main program loop to drive the robot towards the beacon. When the relative distance between the robot and the beacon is less than 10, the robot action stop is yielded. Whenever control is passed back to the update action generator, the MQTT and beacon mode code blocks are re-executed. I've provided some reference material on PID controllers in the README. We've set up the EV3 brick, motors, sensors, constants, variables, and the MQTT connection. And define the update action generator. Now let's look at the main program loop that balances the Segway. The main loop starts by checking if the battery voltage is greater than 7.5 volts. Otherwise, motors will be underpowered for any movement. If the voltage is less than 7.5 volts, code execution stops by breaking out of the main program loop. The next step is to initialize the balancing loop variables. Some of these include resetting the motor rotation angles to 0 and setting the drive speed and steering values to 0 before receiving updated values from the update action generator. The balancing loop is nested in the main program loop. And as the name suggests, this is a block of code that calculates the output power for the motors to keep the Segway balanced when in motion or in a stationary position. Afterwards, the update action generator is called, but not executed. This is on line 223 on the program. This is similar to the simple script we looked at earlier to explain Python generators. The function body is only executed towards the end of the balancing loop, where the next function is used to obtain the next drive speed and steering values yielded from the update action generator. The next thing we need to do is to calibrate the gyro offset. The initial gyro-sensor offset is calculated before stepping into the balancing loop, which is this section here. Gyroscopes are susceptible to drifting, which can cause the measured rate to return a non-zero value, even when the sensor is stationary. This non-zero value is the gyro offset, and this value will need to be maintained in the balancing loop to adjust the gyro-sensor value to get more accurate readings. We've calibrated the gyro offset. The next thing we need to do is to obtain the robot's body angle and rate, as well as the wheel angle and rate, which are needed for the control feedback calculation. The robot body rate is the angular velocity or speed of the gyro sensor, and its value is augmented with the gyro offset. The robot body angle is obtained by integrating the robot body rate over the average loop control period. There's more detail on this in the README and the code. The wheel rate or motor speed is calculated using a moving average of a 4-item list of motor position changes, while the wheel angle is obtained by integration. Again, to keep things a bit short, you can find out more about these calculations in the README. The next step is to calculate the output power to drive the motors. The control feedback calculation, or the output power sent to the motors, is calculated with this expression. The coefficients of variables robot body rate, robot body angle, wheel rate, and wheel angle were obtained by trial and error. I would advise that you start by only changing one constant in the tuning process before moving on to another variable, and circle back as needed to make further adjustments. A calculated output power is constrained to plus or minus 100%, which matches the range of the method used to drive the motors. The Segway motors are driven at the output power calculated in the respective steering directions. After this, a check is performed to determine if the robot has fallen over. If the output speed is plus or minus 100% for more than a second, the robot no longer balances properly and is falling or has fallen over. If this happens, the motors are stopped and the program waits for 3 seconds to allow the user enough time to put the Segway back in an upright position before the program tries balancing again. In the final step of the balancing loop, the next function runs to obtain the driving speed and steering values for the next balancing loop iteration from the update action generator. That's on line 312. The only thing we have left to do is to demo the different segway modes. We'll start out with MQTT mode for directional control. Let's go back to Node-RED and make sure that the connection to the broker is okay. Now run the main.py script on the segway to balance the robot. We'll send commands for the segway to turn left, forward, and turn right. So let's turn left for 3 seconds. Then move forward for 5. Then right for 3 seconds. Set the control in beacon mode. Let's get the segway balanced again. Turn on the beacon and set the channel to 1. Now we'll bring the beacon close to the segway's infrared sensor and get the segway to follow the beacon as if it's tethered. I hope you enjoyed the video and you were able to, or will be able to, learn a bit about MQTT, Node-RED, MicroPython, basic control systems and more. I just wanted to mention a few things about LEGO Mindstorms before ending the video. LEGO Mindstorms was discontinued back in October 2022, but it has its successor called EVN. I'll include this link in the description for those of you who want to know more about it. Okay, that's it. Thank you for watching and I'll see you in the next video.